Okay, and we're going through some of the errors that came up in the Educake and bond energy calculations questions that you did last week. Okay, so we're going to look at this first reaction between hydrogen and chlorine. And to do this, I'm going to be using some molecular models to try and help us out with this. So I've got a key on the side, so the white semispheres are hydrogen and the green ones are chlorine atoms. So each one representing one atom of each. And so I've got an H2 molecule, 2 meaning we've got 2 atoms of hydrogen in that molecule, and our chlorine Cl2 molecule, so 2 chlorine atoms in that chlorine molecule. So these are our reactants, and they're going to start off with an energy. And what happens is when we break these bonds, we have to put in energy. So we're taking in energy in order to break these bonds. And these then at the top of our peak of our reaction profile is our broken compound. We then, as we make our new bonds, so our HCl molecules, we're then going to be lowering our energy, as when we make bonds we actually release energy in doing this. Pulling apart the bonds, that requires energy, but putting the atoms together, that's favourable, and so we release energy to then form our products. Now, without data, I can't tell you whether it's exothermic or endothermic, but that's what we're going to come to in a minute. But we've now formed our products, our 2 HCl molecules. So you would have noticed that I made 2 HCl bonds as we went down our slope, and going up we broke the HH bond and we broke our ClCl. So when we're laying out our workings for this, I always think it's best to separate it out into bonds broken and bonds made. So our bonds broken, we broke our HH bond and we broke our ClCl bond. So one of each of those. And then our hydrogen chloride molecule, we had to make the HCl bonds. But as we formed 2 molecules, you can see we've got 2 bonds that need to be made. So now we can refer to data, which I've got on my computer screen, that you will have had with your question. So the bond energy for HH is 436 kilojoules per mole, and the ClCl is 243 kilojoules per mole, and our HCl is 432, but we're doing 2 lots of that. So just be clear that this is 1 times each of those, but 2 lots of that 432 kilojoules per mole. So then when we're looking at our bonds broken overall, we're going to add up just as you would in maths, 436 plus 243, and so that gives us 679 kilojoules per mole, and here 2 lots of that 432 is going to be 864 kilojoules per mole. So that's our overall energy for bonds breaking and our overall energy for bonds making. What we're trying to find out is our energy change, so the difference between our reactants and our products. We sometimes use the symbol delta H, and our energy change we're going up with our reactant's energy, but down with our product's energy. So we're going to add our bonds broken, but we're going to subtract our bonds being made. So delta H, our energy change, is equal to our bonds broken minus our bonds made. So here we've got 679 minus 864, and that gives us minus 185 kilojoules per mole. Really important to remember to include our negative sign, as this is what tells us that it is an exothermic reaction. As it tells us that overall our energy has decreased going from reactants to products, and energy has been released to surroundings. And we can say that the energy required to break the bonds of the reactants was less than the energy released to make the bonds of the products. And just while we have a reaction profile in front of us, I just wanted to review our activation energy. So remembering that it is the difference between our reactant energy and the top of the peak. So if we were to read off an energy here, our activation energy would need to subtract the energy of the reactants in order to get that difference in energy on our reaction profile. So our activation energy goes from the reactants to the top. So in order to get our value of our activation energy, we read off where the top is and we subtract where our reactants is. Okay, so we're going to take a look at another reaction now. So this is going to be between nitrogen and hydrogen. So these are our reactants for this reaction, and they are making something called ammonia, which is going to be our product of our reaction. So again, I'm using some molecular models to help us with this. My key is at the side, so the white semispheres are the hydrogen and the blue ones are the nitrogen. One thing to notice about nitrogen is that nitrogen has a triple bond, so it's got 1, 2, 3 bonds holding those 2 nitrogen atoms together, and we often draw it like this to show that there are 3 covalent bonds between those 2 nitrogen atoms. Our hydrogen atoms, as we've seen before, still just 1 single covalent bond between each of the 2 hydrogen atoms. So to start with, our reactants have a certain amount of energy. So I'm just going to draw a line here. So that's our chemical energy stored in the bonds of our reactants. So they're starting off with that energy. Then we're going to be breaking these bonds. So we're breaking 3 hydrogen bonds because we've got 3 molecules each with a HH bond. So 3 of those break, and to do this we take in energy. We're then also having to break this triple bond. Now even though it's a triple bond, we still just call it breaking one bond, but it's one triple bond that we're breaking. So again, that takes energy to do, and so we're now at the top of our reaction profile. We've broken all our bonds, and so now it's time to start making the bonds of our products. So here each nitrogen is bonded to 3 hydrogens, so one nitrogen makes 1, 2, 3 nitrogen-hydrogen bonds. So in one molecule there are 3 nitrogen-hydrogen bonds, but we're making 2 molecules. So in total we end up making 6 nitrogen-hydrogen bonds due to the 2 molecules that we've made. And making bonds, we know this is an exothermic process. It releases energy to form our products. Again, without data, I don't really know whether the products is lower or higher than the reactants until I start looking at numbers, which is what we're going to do now. But remembering that we're looking at what our change in energy is between our reactants and our products. So again, setting up our working so that we've got our bonds breaking on one side and our bonds making on the other side. So we said we were breaking 1 nitrogen triple bond between the 2 nitrogen atoms and 3 hydrogen-hydrogen single bonds between each of the H2 molecules. And our bonds making, we said in total we've made 1, 2, 3, 4, 5, 6 NH bonds. So now to bring in our data, which we have in the table from our question. So the N triple bond N is 945 kilojoules per mole, and our HH we're going to be having 3 lots of the 436 kilojoules per mole, and for our 6NH we're going to be having 6 lots of our 391 kilojoules per mole. So then we need to add up these numbers to get our overall. So into our calculators we've got 1 times 945 plus 3 times 436, and that gives us 2,253 kilojoules per mole of bonds breaking, and our bond making energy released is going to be 6 times 391, which is 2,346 kilojoules per mole. So then what we're going to be doing is finding out our energy change, delta H. So delta H, our energy change, is equal to our bonds breaking minus our bonds making. So that's going to be 2253 minus 2346. Which is minus 93 kilojoules per mole. Again, remember it's really important to include this negative sign, as this is what tells us that it's an exothermic reaction. Therefore, our energy is going down between our reactants and our products. As energy is released to the surroundings, and we feel this as heat. And this is because our energy required to break the bonds was greater than the energy, it was less, sorry, than the energy released on making bonds. So energy required to break is less than our energy required to make, therefore it's exothermic. Now, one of the interesting things about the reaction we've just seen is it's actually a reversible reaction. Now, we'll do more on reversible reactions in year 11. However, essentially, as the word reversible means, it can go one way, but it can also go backwards the other way. So we can take what was our products, our ammonia, and we can go back to what was our reactants, our nitrogen and our hydrogen. But as we're going backwards, it's a backwards reaction, and we're starting with this. So in this reaction, this is now our reactants, and this is now our products. So we're starting again with our energy of our reactants. We are having to break these nitrogen-hydrogen bonds. So that's 3 bonds broken for one of the molecules and 3 bonds broken for the other molecule. Just want to keep these bonds with the hydrogens, otherwise when we come to make them we'll have too many bonds or too few bonds in some of our atoms. So we've now broken 6 NH bonds. So that's taken energy in order to have to do that, to get to this state. But now we're going to be making our nitrogen and our hydrogen. So our nitrogen, you'll remember from a minute ago, has a triple bond. So 3 covalent bonds, but we say we're just making 1 triple bond, so 1 N triple dash N. And then our hydrogens pair up, so 1, 2, 3 molecules of hydrogen made. And when we are making bonds, we actually release energy. And so going down, it's an exothermic process, we're releasing energy. Now, I've drawn products slightly higher than our reactants, as because we've already done the forwards reaction, I know what I'm expecting from this reaction, and that's that it's going to be the opposite. So if the forwards reaction is exothermic, our reverse reaction is going to be the opposite, and therefore endothermic. But we can show this by using our bond data. So we're still going to show our workings using our bonds breaking and bonds making. So this time our bonds breaking, we had those 6 NH bonds that were broken, whereas our bonds made, we made 1 triple bond and we made 3 hydrogen-hydrogen bonds. So looking at our data in our table, we're going to be having 6 times 391 kilojoules per mole and 1 times 945 kilojoules per mole and 3 times 436 kilojoules per mole, and then we're going to add these to get our overall for our bonds breaking and our bonds making. So here the 6 times 391 gives us that 2346 kilojoules per mole, and our bonds making, we're adding the 945 plus 3 lots of the 436 to give us 2253 kilojoules per mole. And so now when we're looking for our delta H, our energy change, we're still doing our adding, our bonds breaking, and subtracting our bonds making. So bonds broken minus bonds made. So then carrying our numbers forward, so that's 2346 kilojoules per mole broken, but 2253 released. And this time it gives us positive 93 kilojoules per mole. And so now we see why it's important to have that positive sign, because now it's showing us that it's an endothermic reaction. And so energy is taken in. And we'd feel colder temperature if we're taking in heat. And so then our reason for this is that our energy required to break bonds was greater than our energy released when bonds are made. Okay, one of the other things that came up in our Educake was the required practical. Obviously we haven't done the required practical. I talked through it in one of my earlier videos, but I just want you to try and understand why we use a polystyrene cup to do our reaction in, but also why we then put it in a glass beaker. Now, polystyrene cups, they are, I don't have one unfortunately, but they're much more insulating than glass, and so by having it insulating, we're keeping the temperature of the reaction mixture within that cup so that we can record it to see whether the reaction mixture temperature increases or decreases. And having an insulated polystyrene cup means that it's kept in a more closed system, so it's not going to have as much impact as to what temperature the room is. It will be focused on the temperature of the reaction mixture, whether it's increased if it's an exothermic reaction, or decreased because it's an endothermic reaction. But we then take that polystyrene cup and we put it in a glass beaker. The reason for this is the stability of the glass beaker compared to the polystyrene cup. Polystyrene cup is a bit like plastic. It's really easy, as you can see, for it to fall over. Our glass, not so easy, doesn't fall over very easily, and so we're not going to be knocking that over as easily as a polystyrene cup would. So putting a polystyrene cup inside a beaker, that gives it the best stability. Okay, so I'm going to leave you with 2 questions to have a go at. So calculating the energy change of the following reactions: 2H2O goes to 2H2 plus O2, and CH4 plus 2O2 goes to CO2 plus 2H2O. I'll put the bond energies that you'll need in the comments of the description of the video, and it will also be in your instructions for this week's work. If you're feeling confident, have a go at the extension, drawing the reaction profiles for the reactions, labelling the energy change and the activation energy, making sure to use single-headed arrows so that you're showing the positive or negative direction of the energy change, and also you could annotate the slopes to describe what's happening in terms of energy and in terms of bonds. I'm going to leave you with these tips, thinking about the layout of your working, looking at the numbers of molecules you have, draw out the structures to make it clearer as to how many bonds you're making or breaking. Some exam questions do this for you. However, if like in the Educake ones they're just giving you a balanced equation, then maybe it's a good idea for you to draw out those structures so that you can see what bonds are involved. Things to remember: we're calculating the energy when we're breaking all the bonds of the reactants and making all the bonds of the products in the reaction. Remembering breaking bonds requires energy, so it goes up in our reaction profile. Making bonds releases energy, and so it goes down in our reaction profile. Thank you for watching.